Okay. So, welcome back for this afternoon session. My name is Lars, and I'm one of the professors with a joint appointment in the College of Optical Sciences and in the College of Medicine. And I'm going to be telling you a little bit of a story that will ultimately will come back to my favorite topic, which is medical imaging. But it's going to be the story about the development of imaging as a science. And we're going to spend a few minutes as we go through sort of discussing, what makes a discipline a science, and then sort of look at what it is special about image science programs. What is it that they bring? What perspective is it that they bring? So imaging, I will say imaging is by its nature interdisciplinary. So Dean Koch identified image science as sort of one of the four key areas in the College of Optical Sciences, meaning that there's a significant number of faculty who spend their research lives and teaching lives addressing topics related to imaging. And so let's spend just a minute to realize that, first of all, although it's one of the four disciplines in the college, imaging by itself is always interdisciplinary. So it's drawing and connecting with the other areas. In fact, all of the other disciplines, as well as many engineering topics, electrical, mechanical engineering, and systems engineering, and everything you can think of. So imaging generates data, but it generates data in a particular way. It generates it so that there's an object or a source of light or something that you're interrogating, and it's going to map that onto a detector system in such a way that there's a preservation of spatial information. So you can generate a connection between objects in your data space, perhaps not right away, perhaps some reconstruction is necessary, but you can make a connection between a two- or three-dimensional object space and get it into an image space. Imaging covers the full range of wavelengths in the EM spectrum, everything from the very longest wavelengths to the very shortest. Gamma rays with wavelengths that are getting into a tiny fraction of the diameter of an atom, to wavelengths that are as long as the desk. You can make use of multiple attributes at once, and in fact that's getting more and more common. It's relatively rare that you only work with a single attribute. You might have wavelength and polarization. You might have you might be making use of entanglement. The source, the imaging might be coherent, it might be incoherent. Just about every property of light that you can think of can be invoked in the creation of an imaging system. There's a broad range of fields that make use of imaging. Obviously, Dean Koch referred to the cell phone camera as the one that we all carry, imaging system we all carry around with us. The second one, the first one, of course, is in the human visual system. But the applications that are funded and being worked on in the college, everything from homeland security issues, environmental monitoring, machine vision, self-driving cars eventually, consumer devices, biomedical and medical imaging devices. And I'm going to stick primarily to systems that are not directly using visible light, because you'll get a talk from Professor Barton later on in the afternoon. She will focus on imaging in the visible wavelengths for medical purposes. So this is sort of going to be an overview of the talk, and I'll start a little bit about the setting up the discipline of image science as it's evolved with the history. And it doesn't go back as far as you'd think, the concept of imaging as a scientific area of its own or a discipline of its own. So we'll actually be able to identify a pretty clean starting point when image science sort of came into maturity. And I'll talk a little bit about what the activities are here at the College of Optical Sciences. There are other image science programs springing up across the country. We'll give some examples of images and imaging systems from modern imaging systems, and then we'll talk a little bit, as I said at the end, about what makes imaging a science. So that is my overview, and there is a little guy up there. How many of you recognize what it is? If you're from this area, recognize it as a bobcat. So it's not a domestic cat who's in big trouble. He's a wild cat. He's still in big trouble. This is out in the desert pretty close to where I live, and it's a good slide to entitle Overview because he's up there. So here's a fact that I wonder how many of you know. How many of you have heard about Hazen? So pretty remarkable scientist, pretty remarkable dates, pretty remarkable life, right? So this is the golden era of Islamic science in the Middle East. He lived in Cairo and did most of his work in the Cairo area around the year 1000 AD. And many people identify Hazen as the first true scientist. And certainly he was the first one whose writings about optics survived. So he wrote a book, and it survived all the fires and all the history. And Hazen's book is, in many ways, a manual for how to perform science. He was a philosopher, mathematician, interested in just about everything, and very interested in light and vision, and did systematic experiments and sort of worked out ideas of the scientific method that still hold today. The idea of create a hypothesis, create a test for it, do an experiment to see if it holds, make observations, try to grow a theory systematically, try to use mathematical reasoning, draw diagrams to try to make explanations. He was working with simple things like candles and illumination and casting shadows, and was figured out immediately, the first known person known to be figured out, that what we perceive in our human visual system, by and large, is reflected light. He used candles, and he could block light that traveled to something, and it wasn't visible. He could open it up. You could see it. He could show that shadows were being cast. You could have multiple candles and show that this was an example. He didn't know the term incoherent or coherent imaging, but the experiments, all they did with candles, were incoherent imaging experiments, and it really, in many ways, is the beginning. Now, he used the Camera Obscura and made it actually a fairly popular thing. It disappeared from the history for a while, reemerged in the Renaissance, right? And there's strong theories that the Camera Obscura was, in fact, the thing that allowed the Renaissance artists to really understand perspective. But it was known already 500 years earlier in the Middle East. But even Hazen says we didn't invent this. It goes back much, much longer. In fact, there's evidence that the pinhole camera and the observation that a pinhole will cast of an illuminated object will cast an image through a pinhole onto a wall in a darkened room probably goes back into the cave area. I think the idea is that even some of the early cave paintings were created as a result of images being cast on the walls. Now, even further than that, pinhole imaging goes back 65 million years to this mollusk. That's the first example that I know. I didn't put a slide of that one in. But nature made a pinhole camera with a mollusk whose shell closes up and leaves a little pinhole, and he's got some light-sensitive cells in there. Goes back a long time. Certainly the Camera Obscura goes back to ancient Chinese civilizations long before it emerged in the Western Hemisphere. Hazen also worked out the idea that the eyes were sensors that provided information that flowed from the eye to the brain. And now he didn't have the benefits of sort of modern physiology and to start to sort of understand and be able to probe what the tissues were doing. That began sort of with the idea of anatomy that emerged in the 1540s with Vesalius, who worked out the basic nerve paths of the optical nerves crossing on their way back to the visual cortex in the back of the brain. And why do I bring this up? Well, vision and imaging are tied together. And so anybody have any idea about what percentage of the brain is dedicated towards visual perception, visual of the cortex at least, sort of the thinking and active parts of the brain? Anybody have an idea how much? the estimates vary a little bit. It's right around 30% of the brain is dedicated to visual perception. And of course, the visual cortex is back in the back. We have a very strong instinct to have interactions and responses with data that's presented to us as projections onto the retina. I think I saw the corresponding number for humans for the sense of smell, a little bit less than 2%. So we're definitely respond to images. Now, the idea of taming optics, of course, and I won't go through the entire history here, but of course, the idea of using optics and images for the purposes of drawing inferences about the physical state of things. In many ways, you can point to Galileo and the images of the moons of Jupiter as a key point. Once again, a person of very many interests and talents, a physicist, mathematician, engineer, astronomer, philosopher, and of course discovered through the engineering of an optical system that great truths about nature and the world that we live in could be deduced. And of course, Newton took it further. The next maybe great book on optics, the Newton's treatise on optics, and I will leave things out. I'm picking and choosing here, but of course, the big step forward for Newton was deducing, of course, that white light was a mixture of wavelengths that could be separated with dispersive optical elements, development of new generations of telescopes, and additional work beyond that. Now, at this point, light was still viewed as rays, and the real beginning of modern-day optics can really be traced to the idea of diffraction theory and physical optics as wavefronts. And of course, you guys all know all the names. Just the dates go back into an area of time, sometimes known as the Age of Enlightenment, back in the 1800s, early 1800s, when it really became in vogue to start working in science and making deductions about the nature of things. Some of the key discoveries related to our modern understanding about light and being able to predict how imaging systems work, of course, traced to Fourier. Many people don't realize he was actually a military engineer as well as a mathematician. And Thomas Young, who was a physician and physicist. So all these people have got all these multiple talents. And there was a time when you didn't have to specialize the way we have to nowadays, and you could do both. Now, they were both interested in Egyptology and in cracking of the hieroglyphics and as well. And in fact, Young is one of the people, in addition to the idea about the interferometry experiments and the wave nature of light, and was also one of the two people credited with breaking the code in ancient Egyptian writing. Imaging for the purposes of medical purposes really just traces to a singular moment when they had been playing around with X-ray tubes. There were films and photographic films. Film had been developed in the mid-1800s, right, as sort of the first way to capture an image other than looking through and having a transient copy, and maybe you could make a sketch, right? And it was frustration over poor sketching that led really to the development of photographic film and emulsions as a way of permanently capturing images. But it was really the playing around with the Crookes tube, the vacuum tubes, and of course the accidental discovery of the darkening of a film in response to these new types of rays that were just called X-rays because they seem to have these mysterious properties of being able to penetrate some materials and their ability to blacken film. That is identified as the turning point when the medical imaging began. And of course, William Röntgen was awarded the first Nobel Prize in Physics in 1901. And the story that we tell the graduate students when we go through this is that the time between the discovery that X-rays were able to make a transmission image, for example, through a hand, until the first papers were out and the first actual application in a young boy with a broken leg was like 2 months. So they knew they had something right away. Now notice he was also a professor of agriculture on top of all of these things. It's interesting, all these multi-talented people. So around 1900, all the pieces are in place. There's photography is in place, X-ray imaging is in place. Lots and lots of optical systems are in place, and applications are going. But in terms of the development of imaging and image science, things are relatively quiet for a period of about 75 years. And it isn't that people weren't doing imaging, but they weren't thinking about the quantitative aspects and quantitative analysis and evaluations with using scientific principles, about trying to look at the imaging itself and try to figure out if you were doing that with great fidelity, and how would you measure the information content, for example, that you were able to encode in images. So there was a paper written, Chris Dainty and Rodney Shaw in 1974, that in many ways was the first book that had the title of Image Science in it that started things off. And that sort of set things firing. So after these time period in the mid-1970s, around 1980, so about 5-6 years later, there was the first university department at Rochester, developed a Center for Imaging Science. A journal came out 1984, JOSA A, added Image Science to its title. So now there is a scientific journal for peer-reviewed articles on scientific approach to imaging. Not much later than that, image science started to be added to the graduate curriculum here. It was then called OSC, or the Optical Sciences Center. By the 1990s, there were some new societies and journal in image science developing, and a key hallmark was in 2001, the National Institutes of Health actually opened up an institute, one of the 21 institutes, I think it's 21 institutes in the National Institutes of Health now, is dedicated entirely to biomedical imaging and bioengineering. And since then, things have just exploded. There are numerous other university programs in image science. And as of 2006, there's an optical sciences PhD track in image science that's available here at the College of Optical Sciences. So what goes on sort of in a graduate and research curriculum? So there's about 20 courses in the catalog, in the U of A catalog, that are related to imaging and image science. Not all of them are exclusively the domain of image or image science or interest, but about 20 courses or so are have a connection to it. There's broadly within the college and also spread with these joint appointments, there's about 25 faculty doing research that's would one way or another be considered to be imaging. TRIF is an initiative, it's actually a sales tax-based funding initiative in the state of Arizona that has provided funds and equipment and other supplies and student fellowships in support of imaging. There was a designated component for that. There are also NIH and NSF funded training programs, and there are graduate programs. There is a biomedical imaging and spectroscopy fellowship program that kicks in after the first year that graduate students in optical sciences are able to apply for. And again, there are, because imaging is such an interdisciplinary field, there are people with joint appointments in radiology, pathology, biomedical engineering, electrical and computer engineering, astronomy, applied math, and it goes on and on. Applied physics as well. There's a strong portfolio of grants, and there's lots and lots of student involvement at every level. So here's kind of a quick rundown of some of the courses and the instructors related to those courses. I don't expect to really to read that. But there's a couple of titles in here that are really that underlie the key of what makes a quantitative theory of, well, as soon as I say quantitative theory, that means, of course, mathematics. And so there's the curriculum really considers the physics and the mathematical physics and the statistical mathematics that underlie image formation. And what I hope to convey to you at the end, that image data is inherently statistical in nature, And any inversion process or any other manipulation of image data that you do that doesn't take into account the statistics and the physics of the acquisition process is overlooking a fundamental and a very, very important part of what's needed to be doing imaging in a scientific way. But we'll come back to that. So one of the faculty members here, one of the founding faculty members in the in the Image Science program in College of Optical Sciences, Harry Barrett, wrote together with one of his graduates, Kyle Myers, a very thick, comprehensive text on image science in 2004. Any one of chapter of which is enough for a graduate class and there's a lot of chapters, but so far it's about 5 graduate courses that are taught out of this book. And there's material in there for many more. If you have a chance, if you're interested in imaging, this is one of the books that you should have in your reference library, either in paper form or more likely in electronic form. And in many ways, I will be making references to things in the prologue and in the epilogue and the foundations of image science as sort of guides for what is happening in the field. So one of the things that that makes things a science is that you start to classify things, and so the Foundations for Image Science has, in looking through in the prologue, as it's going to go through and discuss the principles behind a number of imaging techniques and the nature of the data and the mathematical operators that are necessary to understand those imaging methods, starts to divide things up into groups. And there's an old joke out there about there being 2 types of people in this world, those who like to divide people into groups and those who don't, but that belongs somewhere else anyway. So imaging can use principles from or use radiations in the electromagnetic spectrum. But it can also use other forms, seismic waves, water waves, ultrasound, de Broglie waves. What's a de Broglie wave? It's a massive particle of some kind, right? So a massive wave. Particles, neutrons, protons, heavy ions, hard X-rays, gamma rays. You can also do imaging of geomagnetic fields, biomagnetic fields, bioelectric fields, electrical impedance. There is a lot of lots of types of phenomenon, and if we think about imaging of this, establishing a connection between the points in a physical object and points in an image or data space, then these are all areas at which we can accomplish and develop instrumentation and perform an analysis of how effectively the systems work. We can also look at the physical properties that are being imaged. And so we can list the properties as opposed to the technique. We can look at optical reflectance. That's, of course, the basics behind photography, remote sensing, LiDAR. You can look at reflectance in the microwave domain. That's radar, acoustic reflectance, medical ultrasound or sonar for underwater navigation. You can look at source strength, astronomical imaging, fluorescence microscopies. You can look for concentrations of tracers or contrast agents, nuclear medicine, MRI. You can look for attenuation, that's transmission X-ray and film densitometry. You can look at the strength of fields. You can look at electrical magnetic properties, surface heights. You heard former Dean Wyant talk about the WICO systems for optical profilometry, laser ranging, Moiré portography. There is a whole variety just about of physical principles that you can go after in developing an imaging system. Now, how you create the image. So there's one that's not on here, but we can talk about that one. You've got all the optical principles available to you how radiation or things interact to form a constraint or a bending. You've got to do something typically with light in order to create an image. If you don't, all you have basically is an intensity measurement. To establish that connection between object space and the image space or data space, you generally need a physical principle. The one we're most commonly used is refraction, right? The lens of the eye, bringing light back together into a focal point. And all the systems that work can do it with reflection, diffraction, interference. I can do it with scattering. Compton telescope, it works in the high energy domain where you measure the deflection and the energy left behind in that deflection when high energy photons change direction inside a scattering medium. You can do it with modulation of, for example, in a spin relaxation in MRI. You can do it with shadow casting, and I don't see gravitational lensing or gravitational wave imaging on yet. So far, I think we're just detecting them, but you bet eventually somebody's going to want to start to try to do imaging. They already have a rough directionality to it, but somebody will want to make an imaging system out of the gravitational wave detectors. Direct versus indirect. This really has to do with whether you are making a direct measurement of what we would call an image, or whether you're acquiring data that has to be processed somehow to put it back together before we have an image. So direct, well, the human eye, obviously. You get an image on your retina. You get some electrical signal that the brain has figured out how to interpret, passing through the nerve system. Cameras record direct images. X-ray CTs, all they're recording is X-ray intensities. You've got processing to do to put that back together before you have a reconstructed image of the object that you're trying to look at. And finally, we can talk about whether it's passive or active. And a passive system, I would say, is one that's observational. You simply put your detector out there, you aim it in the right direction, and you acquire signals that are coming towards you. Whereas the active systems are one that you're interrogating somehow or putting energy into the system. Send something out, wait for it to come back. That would be an active system. So natural light photography, that would be passive. But if you put the flash on and fire it off, then you've gone and you've got active imaging. So it's yet another distinction about whether you're putting energy into the system or whether you're just receiving a naturally existing signal that's present. So there are classifications. We'll just look at a few of those as we look through a few imaging systems and look at the techniques. So how many of you have heard about synthetic aperture radar? I think just about. No? Some people have. So synthetic aperture radar the concept of synthetic aperture, first of all, is worth describing. So I think most of you had a class in optics, right? And you understand, you've heard the word diffraction limit used, and you know that there's a connection. It depends on a few things. Depends on the wavelength, depends on the size of some sort of limiting aperture. And if the aperture is very large, that means you can get very high angular frequencies passed through. You can get very high resolution. But if the aperture you're talking about is very small, then simply the physical dimension of the aperture will give you a point spread function, which is large, and you will be limited in the detail that you can see. Now, the good news is that nature is kind to us and says, okay, but if you're clever enough, I'll let you use a system that has a relatively small sensing element of some kind, but if you use it properly, I'll let you and you make the right measurements, I'll let you put the data back together as if you had it, a very large aperture available to you. And synthetic aperture radar is an example of a system in which you're making a series of measurements, and if you record the data properly, and you can even record phase with a synthetic aperture radar, and you can synthesize the waveform that you would have seen if you'd had the entire physical system present at once. This is the basis of a number of astronomical instruments that have put smaller telescopes out widely separated, and then you bring the beams of light in, and you do it with a beam combiner if you want to do it for in the visible or near infrared. If you want to do it in the infrared, most of you have seen the VLA or seen pictures of the VLA, right, out on the plains of New Mexico. And that's another example of a system where you're sampling the field that's present in a larger aperture. Synthetic aperture radar, the classic example is an airplane, or nowadays on drones. It has a transmit and receive antenna that works in the radar domain. You're measuring radar reflections. You're measuring them while you're flying along. There is a time delay between when the pulse goes out and when it comes back, and you keep doing it repeatedly. And at the end, You do a reconstruction technique, and you can actually recover the images that would have been present as if you had a very large, very, very large antenna out there, even though what you had was small enough to be flown on an airplane. You can get remarkable resolution with these now, down on the order of 4 inches or so, about 10 millimeter resolution. So this is just a sample put out there where you can see details, even getting reflections off the propellers, off the wings on airplanes. And there's some interesting things about, and there's quite a bit of computational work and theory to do good synthetic aperture radar. But you can do a lot of things with it. You can fly it not only on airplanes, you can put them on satellites. And so this is actually a satellite image where you're measuring actually the phase. It's a height measurement, and it's looking down on what's north. You're looking straight down from above on the Straits of Gibraltar, and so the Rock of Gibraltar is sticking up right here. So this is Europe on this side. This is Africa on this side. You're looking at the surface of the water as well as the topography of the land. And tell me what you see. What else you see? Look at that. You've got diffraction waves created in water waves where the element that generated the diffraction pattern is the opening in the Strait of Gibraltar. And if you look very carefully, you can see some weak waves heading off in the other direction as well. So it's a pretty cool examples. These are long. Obviously, the scale is very large here, so these are very long wavelength waves in the oceans that have been created by essentially the strait acting as a diffracting aperture for now water waves. It can be used for environmental modeling as well. These are images that come down that are looking at, they're scanning vegetation in Alaska. And of course, climate change and the impact on the environment are a big area right now. So there's lots and lots of work going on looking at changes in vegetation that are going on. So you can look at the redistribution of tree species, for example, in this particular case, going on as a function of time, as a function of short-term weather trends as well as long-term climate change trends. In this case, you're not looking at height profiles. In this case, you're actually looking at the strength of the radar return as a function of the wavelength that's used, which varies. So let's look at a quick taxonomy of synthetic aperture radar. So you're imaging with electromagnetic waves. Its antennas are sending it out. The wavelengths are in the 1 to 3 centimeter range typically. You're measuring the intensity of the microwave reflectance or the surface height. Surface height being coded in the phase. The microwave reflectance in the intensity of the signal coming back. The imaging mechanism, this is interference. You're doing a microwave analog of holography. You're typically, if you want the phase, you have to compare against a reference oscillator on board your flying system. It's indirect. You will not, the raw data will tell you nothing. You have a lot of processing of the signals coming back, and you have to have knowledge of where the airplane or the satellite was at the time that the data was acquired. And it's active because you're illuminating the scene with microwave beam pulses as you're moving along. Now, in working out the imaging properties of synthetic aperture radar, if you're interested in optics, this is the most surprising thing about it. You discover, because of the nature of probing the aperture, that the resolution that the system is capable of giving you is independent of the wavelength of the light, it's independent of the distance from the imaging system to the object, and it's independent of the speed of the source. So it doesn't matter if you're on a slow-flying airplane or a obviously very, very fast-flying satellite. Let's look at a completely different technique. I pulled out, I had a couple of examples of adaptive optics and astronomical imaging, but I know you were going to see that this morning, so I pulled that one out. So instead, let's go look at scanning electron microscopy as another imaging modality to get a quick survey on. So of course, scanning electron microscopy, the idea is that you essentially have a beam of electrons, considered the analogy of light, that are impinging on a sample down here. typically sitting, and the electrons don't like to be in air, so it's sitting inside a vacuum system or a partial vacuum system. You will have a sample down here that's a biological sample or maybe a physical sample of some kind. And in regular scanning electron microscopy, not scanning transmission or tunneling electron microscopy, but in regular scanning electron microscopy, your electrons come down and excite secondary electrons that come off, and you detect those with a detector. And so it's the intensity, the number of secondary electrons coming off as a function of position as you raster scan here. That's what forms your image. In many ways, anything that you can do with visible light, you can do with electrons. You can make lenses. You can do some things with electrons you can't do with visible light. You can accelerate the electrons. Good luck with that with visible light. So why do it? Why go to others? Why blast samples with beams of electrons as opposed to just doing optical microscopy? What is the reason? What is it that the electron microscopies get you that the opticals don't? Yes? Why would you get higher resolution? Why do you get short wavelength? Because it's a massive particle, right? So, yes, the de Broglie, this was the beauty of de Broglie's formulation of a universal relationship between wavelength and momentum. Of course, if your momentum has the advantage of having a massive particle involved, the wavelengths get very, very short. So what kind of resolutions can you get in here? About 1 nanometer is a scanning electron microscope resolution. So well below what you can get to even with the best super resolution techniques in the optics or in the visible domain. But you have analogies. You have lenses. You have the equivalent of electrostatic lenses that act as condensers. You can have you have the equivalent of objective apertures that work on. And again, you have a moving sample stage down here, and a detector for the photons coming off. So what can you see? Well, here's scanning electron microscope images. They're all taken on the same mosquito, and as a function of the magnification. And indeed, you can push to amazingly high magnifications in scanning electron microscope systems, factor 35,000. So you're scanning in. Assume this is the lenslets of the eye of the mosquito, getting in, looking along hair fibers, and getting in and looking down. At 1 nanometer, you have resolution much smaller, of course, than individual cells. That's no problem. So one of the questions, though, about an image like this that I'm going to start seeding in here. Okay, so here we have images of a mosquito, and they're nice to look at. They're kind of interesting. But how do we get scientific information out of these? And in many ways, we have a little bit of a disadvantage here because we like to see stuff, and we understand some things, right? We learned something about the structure of the eye of the mosquito just in this quick look. But if we were to learn something about function, there's work to be done to extract information out of imaging systems. Almost all the time, you've got more, real scientific applications of imaging. There's much more work to be done than just acquiring the image. Sometimes you get the whole story. For example, we can figure out how Velcro works just by looking at the scanning electron microscope. So sometimes the image tells you everything, right? And sometimes it can be remarkable. But in most routine applications of imaging, we have work to do to get from the image data to being able to draw an inference about properties of about the object. Hooks and loops, right? That's Velcro. That's what it looks like. All right, so let's look quickly at the taxonomy of scanning electron microscope. We're looking at electron wavelengths. The electron wavelengths can get very short, fraction of a nanometer. Property being measured is secondary electron emission. Sometimes to get them, there's been a small gold coating deposition down on the object to enhance the likelihood that we get secondary electrons coming out. That's okay. The imaging mechanism is refraction. We focus the electron beam to make a tiny little spot. It's direct imaging. There's a scanning beam. No reconstruction is required, so we simply record the intensity of the secondary electrons as a function of where we are. And once again, it's active imaging because we have to illuminate and excite the object with the presence of the electron beam. Let's look at a couple of modern medical imaging techniques. Here's a few, the big ones that you might, techniques you might get done if you go into the hospital with either a broken arm or some other type of disease that that they decide that they want to do some scanning to try to figure out what's going on with you. And I think most of you are familiar enough with X-ray CT that I won't describe the physical principles of it. There's an X-ray source, there's an X-ray detector, they spin around the body quickly, they acquire projection data from all directions. You do a reconstruction with some pretty sophisticated math nowadays, and you get cross-sectional images. So this is one such image. When a medical imaging professional, a radiologist, is reading your films, he's scanning through one of these slices about every millimeter along the length, and he'll do it in one direction this way, he'll scan in the other direction. In this case, we can actually see that there's a problem. How many of you can see that there's a problem? Somebody sees the problem? What's the problem?
Well, it looks like
There looks like there's a lesion in the liver, yes. Most of the time, we'd be probing around. If you're not a radiologist, you'd be probing around looking here, well, I wonder, maybe that should be there, maybe it shouldn't. Actually, it's pretty subtle for most conditions, other than broken bones. It's not at all. If you haven't been through a residency as a radiologist, you can be spending all, you'll see all kind of, well, I wonder if that should be there, All right. So it's interesting. So I'll take an aside here to tell you that when physicists work on building medical imaging systems and looking at the data, I sometimes liken that to, we open up a book, we look at the printed page, the letters are nicely arranged in lines. I can clearly see the difference between an E and an F. This is a strong medical imaging system. This should be good. The physician opens it up and says, it's Moby Dick. So we're not quite talking the same language. The good news is that the ability for the physician to say it's Moby Dick, in other words, interpret the medical story of what's going on, is related to what the physicists are developing the instrumentation to be able to do. But there's another layer here. So whenever anyone tells you, oh yeah, radiography and images are going to be read by computers in the next, yeah, maybe, right? There's a fish, there's a boat, so it's got to be well, maybe it's Old Man in the Sea. The physician is doing a lot of stuff that of the things that humans do really well. So what's happened in image science-wise? Well, the resolution has gotten amazing. So you can zoom in on a bone now. You can look at the trabecular bone structure, which is this sort of thin network of bone structure we have to make our bones lighter. We have this trabecular bone network that's inside. This is an area that's a problem. If you have osteoporosis and you start losing the calcium out of the trabecular bones lose strength. You can now get to amazing high resolutions, fractions of a millimeter, few hundred microns in resolution inside bone systems. But in order to get high resolution, you often have to use a fair amount of X-ray dose. And so there's this growing question nowadays about, well, how much dose is it worthwhile in order to be able to get however good a quality of image? And this is the image science is a lot of it is about figuring out, well, first of all, what is meant by image quality, and we'll come to that at the very end. I'll talk a little bit about SPECT and PET as we go here to give you a little bit of a picture of the other types of modalities. So molecular imaging is a technique in which you apply radio-tagged radio tracers, radioisotope tracers, inject them in very tiny amounts. Tiny because you don't want the tracer to affect the target or the organism in any way. But this is a hot area right now because you have tumors or other tissues with receptors on them. If you can label antibodies or antigens towards those receptors, and you inject them and they distribute, and then the radioisotopes decay and emit gamma rays, then you can image where they went, and you might see the presence of one set of receptors and be able to distinguish against the presence of another. And this is, as you might think, one of the hot buzzwords in cancer therapy right now is immunotherapy and radioimmunotherapy, and figuring out where are these immune cells going is an absolutely key task. So the medical imaging instrumentation for molecular imaging look just like the white instruments, nice white plexiglass fiberglass covered instruments. They all look essentially the same, whether they're doing MRI or CT or SPECT or PET. But the modern ones are doing two modalities at once. They do PET and CT, so you get an anatomical scaffold from the CT, and then you get a functional image from the PET image that's telling you, aha, here's a tracer that's indicating, for example, a high level of metabolic activity that's suspicious for a cancer. And in particular one, the malignancy, one of the hallmarks of a malignant tumor is that it consumes a lot more glucose than normal tissue does. So where does image science come into play in all this? Well, here's an example. Here's a SPECT system. SPECT and PET are different only in that SPECT requires the presence of a physical collimator to create the image, and PET doesn't. It requires many more detectors instead, drawing a line between them. But I'll ask you a question. If we've collected a bunch of image data, and I take it off onto a computer workstation, and I start running my favorite image processing algorithms, can I add anything to the data? Can I add anything to the image? I take it into Photoshop, and I crank up the contrast. Have I accomplished anything that's to add information into the data that's been acquired? The answer to that is absolutely not, except in one circumstance. If, as part of the process, you're adding in knowledge about how the acquisition occurred, so knowledge about the point spread function, knowledge about from a different modality, then you can add data. But basic things, adjusting the Windows thresholds and running filters and edge enhancement and blah, 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 and blah, 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 they're all about the human visual system liking the final image, but you have not actually changed the information content that was present. So when the computer algorithm is going to look at the data, it doesn't want you to do anything. Don't even reconstruct it. I'll just take the planar projections and work on that. But if you add information based on your knowledge of how the imaging system acquired the data, based on your knowledge of the physics of how photon trajectories have worked out, then you can do some amazing things. And you can go, as you start increasing the sophistication in how you incorporate other information or your knowledge of how the system worked, you can go from very noisy, almost uninterpretable data using sound statistical techniques and arrived at diagnostic data that is much more suitable for an observer to draw inferences from. So this idea of somebody, an observer, a human, a radiologist, perhaps a computer. Taxonomies of SPECT CT systems, types of radiation, X-ray, gamma ray, properties being imaged, attenuation coefficient for a CT, radio tracer concentration for a PET or a SPECT image. The mechanism of imaging is always an intensity or a flux measurement. CT, you can't really photon count yet. They come too fast. But for PET and SPECT, you count the number of photons per second per unit area that are arriving. In CT, you measure total energy that arrives per unit area, per unit time. Electronic or physical emission for PET or SPECT. For the imaging mechanism, for CT, it's just a line of sight between the source and the detector. Direct versus indirect, they're all indirect because we have to do tomographic reconstructions before we can see an image. Passive versus active. They say active for CT. Sure, you turn the X-ray source on outside the body. They say passive for SPECT and PET. Well, kind of, because you had to inject a radioisotope in order to get a signal out. So it's kind of pseudo. So I put it in italics. A lot of work in image science is about improving technology. And here's, I chose one out of our laboratories to describe to you because it allows you to see something that's pretty interesting. So scintillation crystals are used when you want to image gamma rays, or X-rays for that matter. The reason is that silicon light sensors like you have in your cameras are profoundly insensitive to X-rays or gamma rays. Or let's say the other way around. The X-rays and gamma rays tend to blast right through a CMOS or a CCD sensor. They don't even bother. They don't even see the silicon. You might as well put a piece of paper in front because the silicon is too low in atomic number. So usually what you do is you put an intermediate converter element in place or a converter material, and that's if it's something that takes gamma ray or X-ray energy and turns it into visible light, then we call that a scintillation crystal. So one X-ray or gamma ray coming in will generate a little visible light burst because it's thousands of times more energy in a gamma ray photon than it is in the visible photons. So every one of the little dots you see in here on this frame. So this is a camera that has a scintillator in front. And now we've added an optical gain stage. And this is such a simple idea. What kind of optical gain? Well, this is just an image intensifier from night vision goggles, basically. In fact, they tend to be military-grade night vision goggles, tend to be, or the intensifiers from those, tends to be the element of choice. And so now we blow up the tiny little bursts of scintillation light, which may have a few hundred visible light photons in them. We put a lot of gain on them, and now they turn into bright spots that we can see on a regular CMOS sensor, just like your video camera. Literally, this could be your cell phone camera running because of the intensity gain from the image intensifier. Every one of the little dots represents a gamma ray interacting in the crystal. And we do the same trick that they heard about in the super resolution. So for every one of these little images of a gamma ray, we'll figure out where the centroid is. And now we get a much higher resolution image because there's like a point spread function, and we find the center of the point spread function, and that beats the resolution limit. So you can get to about 25 microns or so resolution for a gamma ray energy. And that's pretty cool because you can see some interesting stuff. You can see little moons around a lot of the interactions. So a gamma ray in this case has come in and interacted in the scintillator and deposited its energy. Along the way, it's generated a secondary K X-ray, and it's traveled on its own a short little distance. So this distance in here is about 50 microns, so that gives you the scale in here. And so you can find all kinds of interesting new physical effects where you can see the nature of the energy deposition in the scintillation crystal. This was revolutionary. It's only literally a couple of years old. And so there's lots of work now being able to figure out, so what can we do when we really can see the gamma rays individually? Well, one thing we can do is we can set up an experiment so I can show them to you here. So here's a simple little setup. So we have a scintillation crystal, we have an image intensifier behind it, we have a lens coupling system, and we have a regular commercial grade CMOS movie camera, a little thing about this big. It's not an action cam, a GoPro, but it could have been. And we're going to I'm going to put a radioactive source in here that's sending a stream of gamma rays out, and they'll be interacting in the crystal. And I'll show you what happens. So here is a plot of the distance away from the face. And this basically is a plot of, as the light spreads, it gets a little bit blurrier. So look down in this area down in here. You guys get to see when I do that. I'll run the movie. If I run the frame slow, what you see is the same thing as if I took a flashlight and shone it up into the night sky. Photons are going to scatter off dust particles, and you'll see a flashlight beam pointing up into the sky that looks like this. You see Beer's law here. A lot of photons get absorbed early in the crystal, and then they diminish, and so there's a smaller intensity at the back. So the gamma ray beam is coming in from right to left, and a lot of interactions early on. If I start running the frame fast, I get to see individual gamma ray photons, one by one. Okay, I'm not seeing the photon itself. I'm seeing the flash it generated when it interacted and gave up its energy into the visible light photons. And I don't know of any other experiment where you actually get to see individual photons one by one, as in a sense where you can see it. It looks like a beam of them passing, right? And when they get stopped and they flash, that's what you see over in here. Okay, so the wavelengths here are really short. There's a fraction of it. And so these guys are very much particle-like, right? They don't really do much diffraction because there's no physical structures that have physical dimensions that are hundredth of an angstrom in size. So we're cheating a little bit. These photons are high energy, very short wavelengths. But you can build SPECT systems using these optical principles and get to some amazing image. You can also do another type of experiment with them where you create so-called autoradiography systems. And this is important for the immunotherapy and radioimmunotherapy. So one of the things about if you're going to tag immune particles, either just to figure out immune system cells to figure out where they go, or molecules of the immune system, antibodies, where they go. You need to figure out where are you putting dose. And in particular, you're worried about liver and kidney, those areas that the body is using to clean out circulating molecules out of the body. And you can do some really neat stuff with this technique with a photon counting autoradiography. And you can see where the particles are being deposited, alpha particles, beta particles, as well as the gamma rays. And if you zoom in on this, because the resolution is so high, so this is a piece of a mouse kidney. This is about this is 1 millimeter diameter in here. You can actually see the structure of the mouse kidney. So these The kidney itself has kind of the filtration regions. And then it has, there's a primary artery and a vein. There must be both an artery and a vein that bring blood into the kidney, and it does its job. And typically what it does is it extracts salts and other things, put it back into the blood, and allows those to continue circulating, but pulls out those things and extracts into the ureter to send down to the bladder, those things that the body wants to excrete. And so if you put too much radioactivity into that region that's doing the filtration, you will harm and create some damage in this. So this allows you to do what they call microdissymmetry, to work out the exact regimens, how much of a particular drug are you able to use if you're going to put a radioactive tag on it, where you can be sure that you don't cause kidney damage. And so that's the type of stuff and the type of study that's very interesting to do as part of the drug discovery process. So what do graduate students do in our laboratories when they work? Well, they build systems. Most of our graduate students are working on an image science principle. They might be a theoretical component, might be a physical component, but a lot of the students build systems, novel systems that exploit new image detector technologies, imaging ideas, or concepts. And this is just a group of some recent graduates and the systems that they built. It was only to give you an idea, what do people do? And this is only a picture of basically what people with our do. One of the things that imaging that we struggle with a little bit is a question, and it kind of comes back to, you saw those amazing images of the mouse brain from Dr. Q. And if you're going to try to figure out how the brain works using imaging as a technique, imagine the following. Imagine that an alien being comes down onto Earth and wants to figure out how a computer works. And you image a computer, take an X-ray of it, and you look down on some big scale, and you discover there's chips, and there's a circuit board, and there's copper traces. Is that enough to figure out how a computer works? No. So now you go, okay, we're going to have to define it. So we go in, we find the chip, a microprocessor chip, and we go in, and now we do really fine, and we go in and we see individual transistors implemented in the silicon. And you see all these transistors. And the question now is, can you now figure out what a computer does? And the question is, now you got too far, because now you're seeing individual electrons and single gates, but you can't get the big picture of software and connectivity and data flowing. And in any biological system, you've got these multiple length scales. You've got to understand the system not only down at the neuron level, but you need to understand how things connect. And the big question is, you've got to understand the software. It's hard to figure out what the software is by taking an X-ray of a computer, right? So there's a lot of work still to be done. But the fundamental question of understanding how things are connected means it implies imaging at multiple length scales. And all imaging systems, basically, no matter what imaging system you have, you fight between this question about resolution, sensitivity, and field of view. And you can change, you can zoom in, and if you get into a microscope, you can get exquisite resolution and high sensitivity, but over a tiny little spot. And so you have a sampling problem. You can zoom back out. Now you're looking at the big picture, but now you can't see the details. So we've been working a lot on how to address this, and our approach has been to build systems at they can image at multiple length scales. So they have zoom, basically, and adaptive. And so now the question is, but how are you going to know where you want to zoom? And so this is the thing that's been a long-term project in our group, is to develop systems where the imager can change configuration in response to the data and figure out where it needs to go in and measure really high magnification data, as well as acquiring the low magnification data that's needed to understand the big picture of what's going on. And so a lot of what's going on in our image science and technology development labs now is really marrying new detector technologies with robotics, with GPU computing, lots of electronics, using all kinds of tools about that. But let's finish up the last couple of minutes here with the really question about what makes image science. Why are we saying that we're not just imaging? Why are we saying image science? Well, there are certain elements of the science that you need to adhere to. And in fact, these will allow you to distinguish against things that are not sciences. And there are always new fields popping up out there that don't follow the tenets of a science. Sometimes they evolve and become science, although sometimes they fade away with a fad. And the first thing is you need a common language, agreed upon set of definitions. People have to be able to talk to each other and understand and have agreed upon things. This is what this means. You don't get to redefine it for your particular application. You have to invent a new word if you want to have something new going. You have to have an accepted set of experimental procedures, and you have to have a theory with predictive value. And the most importantly, the scientific theories are quantitative, they're testable, and they're most importantly, they have to be falsifiable. If you can't declare that a hypothesis is wrong, you don't have a science. You have to be able to do hypothesis testing. So the question is there a theory of predictive value in image science? Interestingly enough, if the goal is to predict the image, absolutely. We have phenomenal computational tools and theories regarding the propagation of radiation, understanding interactions of radiation with matter, understanding how detectors work, being able to model noise. But it's a more complex answer if the goal is to predict the quality of the image that we would. Can we predict the quality of an image that we'll get if we build an image? Well, so we introduced a new term, quality. So we better be able to do this thing about a definition of quality. So here's the thing I want you to take away from image science. Image science begins when you come up with a definition of image quality that withstands quantitative scrutiny. And so the question is, how do you do that? So image quality, in short, after a lot of amazing people have been thinking about the problem, is really about the ability to extract information. And extracting information from an image can be by a human observer, it can be by a computer observer, but the quality of the image has to be defined in terms of the ability to observer to extract information from the image. No other definition of image quality works, even though people like to say, this looks like a high-quality image, because my brain likes it. And so there's a problem there because our brain is just evolved to like certain things, and that's not necessarily scientific. This became a critical question for the regulatory agencies because as manufacturers put out medical imaging systems or other systems, and they come into the FDA and they say, this is the best imager that ever has been made, and the FDA says, according to what metric? And then they say, oh, but we defined image quality to mean the following. And then the FDA goes, yes, but the other manufacturers define it this way, and it just wasn't going to work. And so it was absolutely critical for image science, and it came in just the right time. Back in the early 1970s, the question really came to a head. How is the FDA going to make a decision about whether a new imaging system really is as good as, or even better, than an existing one or another one? And some of these key people, and I'm happy to say many of the people from the image science program are in the FDA applying image science principles to exactly this problem to keep the manufacturers honest, because they will all invent metrics that make their particular system looks like the best one. So image quality must be asked. The question, the definition must incorporate 4 elements. What information is desired from the image? How will it be extracted? What is the observer? What objects will be imaged? What is the statistical variations within the objects? People are individuals. Some people have their appendices on one side. Some people have it on the other. You better have an imaging system that is able to accommodate that, an observer that's able to accommodate that. And what limits the information extraction? What are the sources of noise? Is it fundamental? Are we looking at low photon rates? Are there electronic noise systems? Is there scatter along the pathway? What are the other things? You have to have a complete description of the physics. So you need 4 things: task, observer, object statistics, and image statistics. If you have those, then you can start a process of optimization to build better instruments. And what we've realized, you can also have the methodology needed to do on-the-fly adaptation as for the AdaptiSpec system that I pointed out earlier. That can change in response to the data. Let me tell you a little bit about what's ahead in image science. So systematic task-based optimization of imaging systems. We benefit from the enormous increases in computer power. We're one of the few groups of people, I think, that love gamers. Computing and imaging nowadays is entirely dependent on and benefiting from the development in GPUs, right? And the more gamers want more power, more realistic renderings, the more the technology companies, NVIDIA, AMD, are creating processors that can do things like ray tracing and things in optics. We're just benefiting along the fly with the fact that they want to be able to render realistic-looking scenes It's completely revolutionized computing. No one nowadays writes a scientific article that ends with the words, not computationally feasible. You'd never get, because, okay, wait till next year, then do it, right? It can be done now. No one, in the 60s, just about every paper ended with not computationally feasible. It has changed everything. Huge improvement in sensors, data acquisition, ability to manipulate giant data sets, been able to handle big files. Better understanding of human perception. Believe it or not, the human eye and the human visual system's response can be modeled mathematically. I thought, oh, there's no way when I first came into this field. It's too complicated, blah, blah, blah. No, you can predict exactly how a human visual system will respond to the particular data coming from the system. It's understood. It's channels, and they can model, and they've figured out along the way exactly, well, not exactly how the system works, but how it responds and how humans respond. Computer algorithms to augment or replace the human. Let's go with augment for the moment. The tricky part about computer algorithms is the human is so good at the tiniest little stuff. So we see an image of an apple in the middle of a picture, and we have absolutely no problem with the apple turned 90 degrees sitting up in the corner of the picture. And the computer algorithm fights to be able to accommodate. Or this apple had a little green leaf attached to it, and this one doesn't. There is so much work to do before the computer algorithms can deal with all the slight variations that for a human you don't even see the problem that the computer has a problem with. Integrated computational imaging systems, that means that computers are getting out close to the sensors. No better example than the CMOS sensors in modern cameras, modern lenses, right? You took an X-ray of a modern lens that goes with an SLR, there's more computer chips in it than there is glass, right? The volume, the lens is, a cylinder this size, the lenses in the back are about an inch, and everything else is filled with motors and computer chips inside. And computational imaging up front, it means that you can do data analysis on the fly and not having massive bottlenecks of streaming data that have to get to some other place to be processed. New signals being invented all the time. New technologies all the time. New dimensions. What does that mean? Why did I write that? Call it more new dimensions. So imaging, how many of you have heard about the light field sensor? So the light field sensor measures not only the presence of a photon, because it's passed through a micro lens system, you get information about the direction. And if you know how many photons are at a particular point traveling in a particular direction, now you have the data that you need to be able to refocus after the fact using computational methods. Choose your point of depth of focus afterwards. New pedagogies. Image science is just absolutely exploding right now, to a big extent because of the power of imaging. So with that I will say thank you and take questions. Before that, I will show you how we got from that first slide to this one. And here's how it happened. Quite a bit of gymnastics. Remember, he's high. He's about 70 feet up in the air on top of that saguaro. And those spikes, his poor pads, it must have been agony. But once he's gotten around, so once he's been able to, and at this point between here and here, he was basically flying. Because but once he's here, now he can slide back down and get back down. So why was he up there? That's the big question. Well, he was up there because there was an even bigger bobcat down at the base, and they are territorial. So anyway. But with that, I will take some questions, and I'll let you take your break, and if you...
All right, good afternoon, everybody. Welcome back. It's been a long day. Exciting program so far. So we'll try to keep you interested in all these different things that are going on, the multifaceted aspects of optics. So I'm going to talk about tissue optics and biomedical imaging, a little bit different. So we'll go through this. I'll start with an overview of what tissue optics are, what we mean by that. Then I'll talk about a couple of different imaging technologies. High-resolution imaging, which is basically the microscopies. Then go into optical coherence tomography and optoacoustic microscopy, and then go into, there are some low-resolution optical imaging modalities, optical diffuse tomography and bioluminescence tomography. And then finally, as we have time, I'll discuss therapy. The previous ones of these, you're trying not to damage the tissue. You're trying to interrogate it and get information from it. In laser therapy, you actually intentionally trying to damage the tissue for a therapeutic purpose. Did I see a hand?
Yeah, it's just a quick question. On the first slide, what was, I don't know if the picture was in the bottom.
That? So this is an ovary with our endoscope on it. We're doing laparoscopic imaging. So yeah, inside the belly. Yeah, and that's inside the colon of a mouse, and there we are in my lab. All right, so let's talk about the ideal imaging modality if we're talking about actual, tissue, biomedical, optical imaging. So the ideal modality would give you cellular level imaging or imaging of microscopic tissue alterations, and the reason for this is historical. How is a diagnosis done today? Well, they take a sample of tissue, they either grow it in a petri dish and see if it's bacteria, or they pickle it and slice it thin, stain it, and look at it under a microscope. They're looking for cellular level alterations. So really, if you want to replace that the most easily, then you want to give them something similar to what they've seen before. You want it to provide both anatomical and functional imaging, so about the tissue shape and its function. It should be inexpensive, it should have no harm, minimally invasive, that goes along with the limited harm, deep penetration. We'd love to be able to see all the way through the body with cellular level resolution. That doesn't currently exist, and I'm not sure I see a way for it to. High contrast and easy to use. So this is a combination of optical specifications and also things that come from the medical field. So new optical imaging modalities promise to provide many of these capabilities. We can't always give everybody everything they want. But the advantages of optics for biomedical diagnostics really are that they have resolution, so millimeter to submicron, sensitive to tissue structure and biochemistry, so from which you can get some functional information. They're relatively inexpensive, compared to an MRI machine that can cost $3 million. Optical techniques are inexpensive. And there's no ionizing radiation, which is huge, particularly if you're talking about young children or wanting to do imaging over and over and over again. You don't have the ionizing radiation that you have with X-rays. But there's some challenges. If you want to get high-resolution images, you really just are not going to see more than a couple of millimeters deep. If you want low-resolution images, you can get further than that. You generally have a small field of view. You have this, the number of pixels in an image tends to stay about the same. And if you shrink your resolution unit, you tend to shrink your field of view. Your endogenous contrast, in other words, the contrast you get from the tissue without any stains or dyes added, can be poor depending upon the modality. You don't get these beautiful high contrast images like you get in MRI. And oftentimes it requires training to understand and interpret the results because you get information and it looks like nothing the physicians have ever seen before. All right, so going on to tissue optics, what is it? It's an understanding of the unique ways that light interacts with living tissue as opposed to, say, just propagating it through a crystal. So, one of the interesting things is that despite what I just said, light actually does travel a long way through tissue. So this is one of my favorite pictures of a former mentor who just put a flashlight in his mouth, stood in a dark room, and took a picture of himself. And sure enough, you do see the light traveling, all the way from here up through, especially through his sinuses, right? It's coming out there, and it's a little light in here, but his eyes are kind of ghostly looking too. So, you can get light a long way through tissue, but it's very blurry. You're certainly not getting cellular level information here. It's also looking at the unique constraints of working with living matter. So, this can be good. For instance, this is a picture of the inside of an abdominal cavity where there's all these cancer metastases everywhere. And, if you just look at it under white light, it just looks pink. But if you can apply a special dye that binds to the cancer, all of a sudden, you can get this wonderful image that can do good things. Light can also do bad things. So those of you who have been in Tucson for any length of time know not to do this. So even the sun can burn, and lasers can burn much more easily. All right, so one of the things we really worry about that's kind of unique in tissue is scattering. Because tissue, it's not like even the sky. There are other diffuse subjects out there. But tissue has scattering on every scale imaginable. It goes from nanometers to meters. And I'm showing a tendon here because this is a great example of where you start off with a collagen molecule, and then it wraps up into a fibril, which wraps up into a fiber, which wraps up into a bundle, which wraps up into a fascicle, which wraps up into an entire tendon, which can, run the length of a limb. So the light is going to scatter. Here's an electron micrograph. The light is going to scatter at every single one of these interfaces. There is no way to computationally do this. So I have seen people who have tried doing finite element modeling of a cell. I mean, it's insane. And they're still simplifying things down to, the mitochondria, but they don't get all the, the folds in the mitochondria. So you really have to start thinking of, from a practical matter, if you're looking at a living creature and you're doing imaging in vivo, you just think of tissue as having these bulk properties because it's really difficult to think of it as any other way. And yet when you think of it as just having bulk properties, you've really oversimplified things, and that can lead to some problems. The other thing to remember is that in a lot of biomedical imaging, we are dominated by scattering. Light spreads out in tissue, depends on the number of scatterers, what direction they scatter the light. Light tends to scatter tissue tends to scatter light in the forward direction. And so that leads to some interesting properties. And light also, the scattering decreases monotonically with wavelength. And so you've probably heard of Rayleigh scattering and Mies scattering. Tissue is in between, right? Because it has these scatterers at all scales. The small scatterers give you Mies scattering. The larger scatterers, Rayleigh. So, you can, or the other way around. So you can put that all together. And if you look at this graph, you can see that you kind of have this monotonic drop-off with wavelength. So that means if we want to image, we really want to push towards the longer wavelengths because they're scattered less, and that means we can keep high resolution better for deeper into the tissue. And light scatters very quickly in tissue. So, if you look at optical imaging instruments, they tend to either work in the single scattering mode. This is like microscopy and optical coherence tomography, or the diffuse mode, which are these low-resolution techniques like optical diffuse tomography, bioluminescence. This is only a millimeter, and we're showing just a phantom here with light coming in. In about 100 microns, within 100 microns, you can say, okay, the light's pretty much still traveling in the same direction. After that, it starts spreading out and spreading out. And after a millimeter, it's just a diffuse blob. We call it a random walk. So if you're working here in the 100 micron, you can pretty much assume the light's traveled in the same direction, and you can do some really high resolution imaging. If you're in this increasing photon scattering, techniques like optical coherence tomography do pull out all the stops to extract those photons that are still going in a straight line and reject everything else. But once you get past about a millimeter, all bets are off. You just have to assume that you've got this blob of light traveling probabilistically through tissue. So that's scattering. And honestly, usually in the regimes that I work in, that's really what dominates things. But of course, the other thing that's really important is absorption. So what absorbs in tissue? It really boils down to three things: hemoglobin, melanin, and water. There are others in the body, but these are the three main ones that you come across most often. And so hemoglobin, depending on whether it's oxygenated or deoxygenated, but it's basically red, and so which means it absorbs light very strongly in the blue wavelengths and pretty much not in the red or near infrared. Melanin just kind of, melanin's brown or black, so it might mostly just monotonically decreases with wavelength. Water, on the other hand, we tend to forget that water absorbs when we think in the visible wavelengths, but of course it does. And so it starts increasing in its absorption here into the near infrared to the point where it's not on the chart here, but by the time you get to 2 microns, it's very, very highly absorbing. So we talk about this optical window here between, 700 to 1100, maybe a little bit less, maybe a little bit longer, as an optical window where light can travel long distances through tissue without being absorbed. It's scattered, but without being absorbed strongly. So that's absorption, and absorption is pretty straightforward. It either stops your light and your light is gone, or it doesn't. Another thing that we consider a lot in tissue optics is fluorescence. So fluorescence is not like just looking at the fluorescence of a single chemical entity dissolved in a single solvent, which gives you, very beautiful, bright, strong, narrow spectral lines. When you're talking about the fluorescence in the body, the fluorescence emission and excitation of all these molecules is affected by their environment. And you've got varying environments, varying pHs, varying salinities, varying different things in your body. So it's very messy when you do fluorescence in the body, and you end up with this very broad, diffuse fluorescence peaks. Because fluorescence is a superposition of fluorophores, all the different fluorophores in your body, and it's dependent upon the fluorophore concentration, the quantum yield at this excitation wavelength, the attenuation of the excitation light down to the fluorophore, the attenuation of the fluorescence light back out of the tissue, and the collection and emission light by instrumentation optics. So even though doing fluorescence spectroscopy in tissue is really simple, basically you just dump light on tissue, all the fluorophores emit light isotropically, you collect it back, you send it to a spectrometer. Interpreting those results can be very difficult. A lot of times we try to extract information. So this is just a cell. So this isn't even as complicated as it gets, because these are just cells. We don't have, the whole tissue structure around them. But if we look at, we're going to excite all the way from the ultraviolet up to the green, and we're going to look at the emission here in the ultraviolet out to the red. And so if you look at cells, they have a big hot spot here where you excite them at about 290. And they emit in the ultraviolet. That's from tryptophan, which is an amino acid. You've got another one out here where you excite in the blue, and it also emits in the blue. That's from the metabolic cofactor NADH. We have another little weaker peak here due to FAD that is most efficiently excited, again, in the blue, but it emits in the green. And so you can imagine, this is pretty blobby. And you put that together with different types of cells in different types of structures, and you end up with very broad diffuse spectra. But they do change during disease, and so this can be a very useful diagnostic. You're probably most familiar with doing, getting these kind of beautiful pictures that places like to show. Well, these are dead cells put on a slide and stained with poisonous contrast agents. So these are very beautiful, and for people who want to look at cell structure and understand things that are going on, these are very, very nice. However, if you want to get to FDA-approved dyes, they're all non-selective. Fluorescein, you may have heard of fluorescein angiography, indocyanine green, or ICG, and methylene blue are some of the few dyes that are approved by the Food and Drug Administration for administration into humans for clinical purposes. They do not selectively bind, penetrate the nucleus or bind to the fibers inside of the cell. They just kind of go everywhere. So you can't get images like this in vivo. All right. So one of the other things I like to do when people come to me with a problem and we're trying to look at whether or not optical imaging can solve that problem is to think of all the different imaging modalities that we have on this graph of resolution as a function of depth of penetration. And of course, we really want to be down here, right? We'd love to have subcellular resolution all the way through the body. But we can't. You have microscopy down here. Basically, you can only image thin sections. But it has very high resolution. We'll talk a little bit about confocal and multiphoton microscopy, which allow you to image a little deeper inside this ballistic regime. optical coherence tomography, which you start losing some resolution, but you gain. You can get deeper into that increased scattering realm. And then modalities like photoacoustic tomography and optical diffuse tomography, which do allow you to image centimeters in tissue, but they're fairly low resolution. So please just interrupt me at any point in time if you have questions. Otherwise, I'm just going to power through this. So microscopy, you've probably seen a microscope like this before. Modern microscopes are pretty complicated, but basically you can illuminate a sample from the bottom or from the top, and the light goes back either to an eye lens or to a CCD. And if you look at it, the types of microscopy you have, if you're willing to slice, pickle your tissue, slice it thin, stain it, you can get these very pretty, very detailed images like this. This is called bright field microscopy because you're just illuminating through the slice of tissue. If you want to start doing in vivo, you can do microscopy in vivo. That's what an endoscope is. There's no reason you can't do it, but your images don't look quite so pretty anymore because you're illuminating from the top and the light's kind of scattering around in the tissue. Some amount of it comes back and scatters back out, and you collect it back with, through your objective and to your CCD or your eyepiece. And so you are basically seeing some diffuse scattering around, but the mechanism of contrast here really is absorption, so where the light was absorbed by these blood vessels in the tissue. You can get different types of microscopes, polarization-sensitive microscopes. So again, if you're willing to transilluminate through a thin section, you can get these really pretty images, very beautiful. This is all, a polarized narrowband light image where we're looking at the birefringence of the tissue. But if you want to do it in vivo, your images lose resolution, they look blobby, or you start having the scattering problems there. But you can extract really interesting information. This is some information on skin cancer, where you can't really see much in the regular light, but if you look at the polarized light coming back, you can see the extent of this cancer. Again, fluorescence. If you want to, stain your tissue with these toxic dyes, you can get these beautiful images of cells. You can do the same thing with chunks of tissue. Again, your images are lower resolution, and I haven't false colored these. They're just black and white images, but you can get images of the tissue fluorescence as a function of emission wavelength, and you can see all kinds of interesting things. Like, for instance, here, they're all kind of about the same brightness at 280 nanometers. At 340, all of a sudden, you can't even see that piece of tissue anymore. So you can extract information that way. So that's microscopy. Advanced microscopy, a confocal microscope allows depths below the surface to be imaged. You realize a regular microscope just allows all the light back in, whether it's in focus or not, whereas a confocal microscope allows you to selectively pick out the light that's from your focal volume. And it just does this with a pinhole. You put light from a laser, you focus, essentially a spot from the laser into the tissue. That light comes back, fluorescent light comes back, it's separated with a dichroic beam splitter, goes through pinhole. So light that comes from below the focus or above the focus or has scattered out to the side isn't going to make it through the pinhole with high efficiency. That allows you to get really some very interesting images. This now is it's a rendering of the confocal three-dimensional stack, but you can get much higher resolution images actually of tissues that are still alive. It can also be implemented in a catheter. This is Dr. Art Dimitro's work here, where he's actually designed a little teeny tiny confocal microendoscope here that can fit through a standard commercial endoscope. Multiphoton microscopy, some of you saw one of the systems we've built in my lab today. This is basically where you take light and you squeeze it in time and space to the point where molecules absorb 2 photons of light, thinking it's 1 at twice the energy. And when it emits, then you're actually going to get fluorescence light at a lower wavelength than what you excited the sample with, or you can get second harmonic light generated from collagen. This is actually an image taken by Dr. Con-Q with his 3-photon microscope, which shows in green where we can actually see red blood cells, and we can see all kinds of contrast from the fat through the unique mechanisms you get with 3-photon microscopy. We're trying to take this and turn it in vivo. We have taken our big system, and we can do sterile surgical imaging on that by simply just having a stage big enough to put anesthesia and warming and all the sterile drapes and everything that you need to do surgery on small animals underneath there. But really what we're interested in the future is making a microscope like Art Gemitro's confocal microendoscope and doing this in people. But in vivo, it's maybe not quite as beautiful as some of the other images you saw, but we're getting very good at it. So these are in vivo images with the fluorescence, 2-photon excited fluorescence in the second harmonic generation of the same mouse over time as it's developing a disease. And we can see that the fluorescence gets blobbier and the collagen structure gets more twisted as this tumor is developing. Okay, moving on. So if we progress up that chain and we're getting to optical coherence tomography, the idea here is that we're doing ultrasound with light. So we're putting light into tissue, and we're timing how long it takes to come back out, really the short version of it. And I'd be happy to talk with anybody if you want to get into this in more detail. So this is really good for mapping the microstructure of tissues at the tens of microns capability. It's super robust. You can come by and kick this instrument, and it's not sensitive to vibration, so it's very easily translated into the clinic. And you can get all kinds of lovely details inside of arteries. This is human skin. This is actually a mouse colon here. I've got a bigger picture of a mouse colon. This whole thing is only 0.5 millimeter deep. 30 millimeters long. We're seeing beautiful structures of the crypts inside the colon and all the multiple structures where you actually see through the wall, and you can see things like the small intestine outside of it. If we do this in 3 dimensions, then we can start taking 3-dimensional images, virtually reslicing them. We could render it. We could do anything we wanted. One of my favorite things to do is to just, basically do a fly-through. We're looking at the surface and going down into a mouse ovary. You can actually see the eggs inside of the follicles right there. There's another one there. And we can go in. You start losing your signal. It's getting blurrier and blurrier as we get deeper, and the light's attenuated and scattered. But you can see, in a good 0.5 to 1 millimeter. We can take these techniques and we can put them into miniature endoscopes. Some of you all saw the floposcope in my lab. Here's another picture of it down here. This is 0.8 millimeters in diameter, and it includes both an optical coherence tomography channel and a fluorescence imaging channel. This one we haven't yet taken into the clinic, but we have with our other ones, so there we go. There's our ovary again. Here's the other side of that instrument. That's our physician there holding the probe on his right hand, and that's the woman's belly. She's not pregnant. They just, when you do laparoscopic surgery, they fill your belly with air so they have room to work in there. Fortunately, she's quite normal. That's a normal, healthy ovary. If we want to move deeper, we have to start playing additional tricks and or give up things. So one of the tricks you can play is to combine the good things of both ultrasound and light, and that's called photoacoustic imaging, optoacoustic imaging. It has various names. But if you put light into tissue, a very short pulsed laser beam, and it's absorbed by, say, a red blood cell or a melanin molecule, it will generate a shock wave, and this pressure wave will propagate through the tissue. And it can actually, the pressure wave can be measured on the surface of the tissue. And these transducers could just as easily be on this side of the tissue as well. So theoretically, you can get centimeters deep imaging with high resolution because your resolution is determined by the size of the optically absorbing object and your reconstruction algorithm. But the depth of imaging is determined by ultrasound, which is a lot deeper than light can go. In practice, there are still trade-offs, but you can get higher resolution imaging deeper. The problem is you're limited to the mechanism of contrast of absorbers. But you can get, in some cases, very beautiful images of, here's a blood vessel network with a melanoma embedded inside of that. So 2 things that absorb light, so it gives you the contrast. You notice, these look very different than your other images because you're not necessarily seeing the same tissue structures that we saw. Finally, one of the imaging modalities that really is more like the picture going back to Dr. Tromberg with the flashlight in his mouth is optical diffuse tomography. And there you just give up on ballistic light. You just say the light's traveling probabilistically. You're putting light in, you're measuring it over here. You know there's some probabilistic path from source to detector. So we infer optical properties from surface fluence measurements. And the advantage of this really is it gives you a lot of really good functional information because the absorption of hemoglobin and fat will absorb at some wavelengths. It can give you some structural information from the scattering coefficient. It's relatively cost-effective and portable compared to MRI and CT. But the problem is that it's probabilistic, so you're trying to infer the optical properties of an entire volume of tissue from surface measurements. So it's inherently an ill-posed problem. And so it tends to be low resolution. You tend to see a lot of artifacts. The instrumentation is getting smaller and more compact, and technology is helping a lot with this, but it's still a little bit scary looking, actually. This is a breast imager, and it's always ironic to me when they think that women would rather do this than a mammography. And so, you know, I don't know about that, but it will get better. So we know the probability. We know that light tends to travel probabilistically. We call these our bananas between a source or emitter and a detector. And so if you put a light source here and you put detectors around in a circle, we know the paths here probably won't experience a whole lot of absorption. The paths that go through some tumor will. So the forward problem, dinosaur makes a footprint, right? That's pretty easy. If we know the dinosaur, we can probably guess the kind of footprint it does. The inverse problem is we have a footprint. What did the dinosaur look like? Does it look like this green happy guy here, this slightly angry guy? Does it look like Barney? Or, is it the Tyrannosaurus Rex? Is it the disease? That's really what we want to catch, is this. So there's been a lot of work doing that, and I think one of the things that's really promising about diffuse tomography is this functional information it gets. So even though, a mammogram can give you actually really high, nice resolution images, and there's a suspicious area here. Okay, that's fine. This is an anatomical image. It doesn't necessarily tell you whether that suspicious area is a benign suspicious area or it's a cancerous suspicious area. But if we look at these blobby diffuse optical tomography images, we can see, the hemoglobin is really high. The oxygen saturation is low. The water fraction is high. The scatterer size is low, but there's a lot of them. Unfortunately, that's very characteristic of cancer. Whereas if it was a fibroma or something that was benign, it would be exactly opposite. So now there's a lot of work, doing, okay, this isn't necessarily the best technique for screening the general population, but for somebody who has something suspicious, it can give us a lot of functional information. Kind of another way of doing this optical diffuse tomography is called bioluminescence imaging. You've probably heard of this, or just dark box imaging. The idea being that you can put particularly small animals into a box. They can either have a genetically engineered animal that you give luciferase to and it glows and you measure that, or you just put laser light on the animal and you collect the fluorescence coming back. Either way, we're talking about light that's traveling through maybe a centimeter of tissue, and you're measuring surface fluence measurements, and you're inferring what's going on inside the animal. And so, these are the types of images you get. Typically, because all you get are these blobs, it's combined with some sort of micro CT in order to, it's hard to see much from this image, but if you process it and combine it with a micro CT, you can see that there is a tumor growing inside. So that's, used a lot in just scientific purposes. So I put up here, all the modalities, what their mechanism of contrast is. It varies. Absorption, scattering, and fluorescence. Some of them are just based on scattering, like OCT. Photoacoustic is only based on absorption. So their mechanism of contrast of all these are very different. Resolution goes from submicron up to millimeter-ish. Depth of imaging from, only a thin section or only looking at the very surface all the way up to 10 centimeters. And, they varied in terms of how far they're going to go in vivo. All of these have the potential to be used in vivo, at least. All right, powering through that, that's imaging. So now I want to spend just a little bit of time talking about therapeutics as well. So, really in all those techniques I just discussed, you don't want to alter the tissue. You're hoping that you're interrogating it in a way that doesn't change it at all, right? Because you want to see the state it's in. Photo bleaching is bad. DNA damage would be bad. Heating would be bad. But there are some cases where we actually do want to use light to alter the tissue. And so we can do that generally by increasing the irradiance or the power per unit area. And so that's sometimes done by short pulse durations and a choice of wavelength that interacts strongly with the tissue chromophores. So before, where we were saying, okay, blood absorbs strongly in the blue, water absorbs strongly in the infrared, so you want to work in this optical window. Well, if you want to damage the tissue, probably you want to work where blood strongly absorbs or where water strongly absorbs. There are many applications, and I'll give an example of port wine stains since that's one I've worked on myself. You may know somebody, or you yourself may have a port wine stain. They're fairly common. This person here, fewer and fewer people know who that is. Anybody know who that is here? Gorbachev. Okay, all right. Yeah, he was very famous. He probably has the most famous port wine stain still. His, he was kind of proud of. It really didn't do anything except give him a distinctive look. But they can be both cosmetically bothersome to people. Also, she's at risk as she gets older of having the stain around her eyes getting thickened and actually causing vision problems. And so, there's a lot of interest in how can we treat this. So anybody may recognize this from back in the early days of the laser. Arthur Shallow used to like to go around, taking his laser gun, which was nothing but an optical fiber, and shining lasers at a Mickey Mouse-shaped balloon inside of a clear balloon, and he'd blow up Mickey Mouse. I won't go through this, but if you want to see these balloon pop demonstrations, they're all over the web, and they're fun to watch. We do the same thing if we want to get rid of a port wine stain. We are heating up that colored balloon inside of a relatively clear balloon. So if we think of this is your skin, you have a layer that has, maybe some melanin in it, so that will depend on how much melanin is in the skin, and there's a blood vessel down here that we want to get rid of. So we'll irradiate it with something, in the visible range that's likely to be well absorbed. That light scatters throughout the skin. It heats up the blood. It causes the blood to denature. That heat radiates out a little bit, destroys the blood vessel wall, and then you've killed the blood vessel. So what wavelengths should we use? This is the first question. This is the absorption spectrum of oxyhemoglobin. So what would be the best wavelength to choose? Yeah, 420. You might think that because that's the very peak here. Incredibly highly absorbed. The problem is we also have to consider all the other absorbers, and melanin also absorbs really, really well there. So there's a trade-off. Blue light is also scattered more. So it may be that the light just doesn't even penetrate down far enough. It may be stopped by the melanin, and you don't want to burn the surface of your skin, so you have to be careful of that. It may be that the light scatters so far away that you can't get enough down to the blood vessel. So actually, it turns out that the best wavelength to use is maybe one of these peaks over here, the ones in the green or the yellow, because they're a good trade-off between absorption, enough absorption in the blood to do the job, less absorption in the melanin, less scattering. There's also, I didn't mention this, technology limitations. You can't always get a laser of exactly the wavelength, pulse duration, and energy that you want at any arbitrary wavelength, right? There's a finite number of technologies. Okay, so we're going to put it all together. Light to cure. The laser light propagates through the tissue, and this is going to depend on your tissue properties and your laser properties. All right, so you've got to pick those properly. The light is absorbed in your target chromophore, so this, again, is dependent upon your target absorption and your laser wavelength. The target's going to heat up. So we actually, I didn't talk about it, but we have to pay attention to the tissue thermal properties as well. The heat is going to diffuse through the tissue, which again depends on the tissue properties and your pulse duration of your laser. And the tissue's damaged. So just like cooking, putting a roast in the oven at 200 degrees for 4 hours is not the same as putting a roast in the oven at 400 degrees for 2 hours, right? There's a complex relationship here, so we have to make sure we get that right. This is the stuff that we all deal with, but it's not sufficient. So everybody was modeling this when 20 years ago when I was a grad student. And they would come up with the optimum pulse duration and the optimum wavelength and the optimum this and the optimum that. And they'd go and take these lasers into the clinic, and you'd have about a 25% cure rate. And what they're realizing now, and I leave with this because I think this is one of the really important things, if you work in biomedical optics, you can't get away from the bio part. Because the magic here is that, and then a miracle occurs. Because you have an extent of damage in the tissue, but you also have all these growth factors and these wound healings, and this is all biology. So people realize that you had to take this into consideration as well. Otherwise, you'd kill the blood vessel, and it would just go right back if you ignored the biology. So now people who work in biomedical therapeutic tissue optics take this whole thing into consideration, including also perhaps some drugs that you might want to provide to help with this wound response and other things like that. So here we go. You can have really dramatic results. Sometimes they're incredibly dramatic like this. Sometimes they're less, but still significant. And patients may have dozens of treatments for years. So we're trying to make this a little better for the patient. Nobody likes to get zapped with a laser dozens of times over years. All right. So I'm going to leave with that and happy to take any questions. Yeah. Yes. So actually, that's one of the things that we do in our lab. And the one endoscope that I showed a picture of included both optical coherence tomography to give you those structural images, the anatomy information, and fluorescence imaging, which could provide you some functional information. So the key is trying to find modalities that really complement each other and that are necessary. Otherwise, you just end up with an instrument that's overly complicated. But yeah, you can shove them in. And then you have this interesting optical problem of how do you put light of different wavelengths through the same optical system, or do you just put multiple optical systems and just put them together, physically adjacent, but they don't share. We do a lot of figuring out clever ways of using the same optical path for two different modalities. Yeah. Yes?
What limits the resolution on optical coherence tomography?
So there's two different things. The axial resolution and depth is actually given as a function of the bandwidth of your source. So because it's an interferometric technique, you take light to the tissue, you bring it back, and you interfere it with light that went to a reference arm. So the broader bandwidth of light, the less likely it is, over any difference in path length that those returning wavefronts will interfere. So you can actually get micron or submicron axial resolution in OCT just by having a very broad bandwidth source. Your lateral resolution is just driven by your optics, same as any other microscope. Yeah. In OCT, it's even worse, though, because usually we're trying to get information over, say, a millimeter of depth, but we don't focus track. So we generally want a very low numerical aperture system so that we don't go out of focus very quickly. So it's not unusual to find OCT systems where the lateral resolution is substantially worse than the axial resolution. But then again, most tissues are layers. So the information in the lateral dimension oftentimes it's not as necessary to have as high a resolution.
To you guys today about biosensing. So the research in my lab is basically on sensors and diagnostics. So for the first half of my talk, I'll give you guys an overview on biosensors, what they are, what are the key aspects of a biosensor, what is an ideal biosensor. And then the last half of my talk, I'll actually talk about the research in my own lab, which focuses on optical resonators. Here's a picture. Oh, actually, this is not transmitting. Really? Okay. Okay, yes. So for the last half of the talk, I'll talk about research in my own lab, which focuses on optical resonators. So the specific platform that I use are called microtoroid optical resonators, and there's a rendering right there, so you can see it on the screen. So I'm actually an assistant professor in both biomedical engineering and in optical sciences, and so my work has this biological element to it. Okay, so we're going to start out by saying, what is a biosensor? So typically when people talk about biosensors, there's sort of three different definitions they get thrown around. One is it's a device used to measure biologically derived signals. Another is a device that has biomimetic qualities, so that imitates life, for example, artificial noses. And the third is a device that detects the presence of biomolecules. But the definition that is most traditionally used is the International Union of Pure and Applied Chemistry. And their definition is basically you have an integrated device. It has a biological recognition element, so that's like an antibody, receptor, and it basically can provide you with quantitative information about what you're trying to detect. So there we go. And so there are many different uses of biosensors. So you can see here, you can look at food and quality industries, so that's like food quality. You can also monitor environmental pollutants, biological warfare agents. There's also medical diagnostics, so there's been a lot of talk about looking for biomarkers for diseases. You guys are perhaps familiar with glucose biosensors, and also a bunch of biological assays. So this picture on the right is just saying, like, you can look at particle counts for environmental pollution, for example. So this is just a chart of the global biomedical biosensors market. So there's a key trend. You have an increasingly older population. They have rising awareness of what sensors can actually do for you. You have an interest towards home diagnostics. People don't necessarily want to go to the doctor. They want to sit at home with the convenience of taking a test themselves, looking up their results on the internet, not having to wait like a long time to get lab results back. You have increasing adoption of what's known as personalized medicine. So that's, using perhaps cell phone diagnostics to look at your own biomarker levels and whatnot. And there's a huge projected forecast for how much this market is worth. So this biosensor market is projected to reach $15.4 billion by 2021. So I don't know if you guys can see the slide very clearly, but this is a look into the future, for example, of healthcare and what sensors can do for you. Sensors are basically how you interact with your environment. So this is an example of this lady named Anne. She's 65. She's a made-up person. She has heart failure and diabetes. And rather than putting Anne in a nursing home, this is basically showing how sensors can sort of empower her to live at home successfully. So, she wakes up in the morning. You can have sensors in your floor measure her weight, and that they can transmit that wirelessly to her caregivers. She can brush her teeth. Sensors in the floor can tell her, does she have ulcers and whatnot. Wearable sensors is another big thing in the future. So she has a patch on her arm that can tell her basically things like her heart rate, blood oxygen level, her blood pressure, glucose level. So these are all very, very important characteristics to know. So later on, sensors in the floor can tell her, look at her gait, can tell her if she's about to fall. Falls are one of the leading causes of death of the elderly. She can have a sensor in her pill that can tell her, did she actually take her medicine or not? And all of this data can be wirelessly transmitted to caregivers, so people can know what Anne is up to. And so this is really the future of healthcare. Biosensors have a huge impact. So this is, as we were just talking about, like at the bedside, at medical emergency sites, medical labs, home-based medical care. So this is really a field that impacts a lot of different aspects of the population. And so this is just a chart that basically shows you what percent of the market is captured by different applications. So you can see biodefense is only 2.6%. Environmental monitoring is a bit larger, 12.6%. Really, the largest market you see here is this point of care diagnostics. So you can see this in terms of a lot of what's coming out of this mobile phone technology, cell phone diagnostics sort of stuff. And because this is sort of a workshop on optics, so we can pointing out what is the global biosensors market share based on different technologies. So you can see optical biosensors capture a small bit. Electrochemical is very popular. This is basically essentially your glucose sensor. So it's one of the most successful commercial sensors out there. Okay, so this is an example of one of the earliest examples of a sensor. This is known as a canary in a coal mine. So basically, miners would carry canaries down into coal mines, and they would die of carbon monoxide poisoning, which is rather unfortunate for the canary, but it would give the miner an early warning to exit. So this is one of the earliest examples of such a sensor. So we're going to talk today about affinity biosensors. So they're basically devices in which you have receptor molecules. They bind analyte molecules. This causes a change that's detected by a transducer element. So your transducer element is going to basically convert your biorecognition event into, for example, like an electrical signal. Your receptor molecules, as I mentioned earlier, they're things like antibodies, nucleic acids, hormone receptors, and they're most often used to detect molecules of biological origin based on these specific interactions that you have. So biosensors have several key components. One is that you need an analyte. That's what you're trying to detect. It has a receptor. That's your molecule that recognizes your analyte. A transducer. So this is what is basically converting your biorecognition event into some sort of measurable signal. You have electronics, which basically is going to process your signal, amplify it, filter it, whatnot. And then you have your display. This is your end user readout. So it's going to be some quantitative number that you get at the end. It's going to be a number, a graph, a table, an image. Okay, so graphically, these are sort of the elements of your biosensor. So you have samples. So this can be taken from cell cultures. You can take blood, urine, saliva, tears, anything that might have whatever your analyte of interest, your biomarkers of interest. You can have food samples for when you're looking at food quality. And you can have environmental samples looking at your air quality, your water quality, soil, vegetation, whatnot. Then you have your transducer elements, which are composed of your bioreceptor and whatever sort of electrical interface, for example. So you could have whatever we just mentioned, like antibodies, cells, nucleic acids, and they're going to be combined with something that's going to transduce this event into some sort of signal, for example, an electrical signal, and then your signal is going to be amplified, it's going to be processed, and then you're going to get a display. So these are the key elements of a biosensor, typically. And your key characteristics of your biosensors, you want something that's sensitive. So typically when people characterize a biosensor, they want to know what is its sensitivity, how selective it is. Selectivity is very important because you only want to detect what you're interested in detecting, not a lot of things that are in your background. You want it to be reproducible. You want a sensor that's very, very stable. You want it to have a linear response. You want to know what its resolution is, and you want to know what its response time is. So these are all the characteristics of your biosensor that you're typically asked about your biosensor. So there are a lot of challenges, actually, in biosensing research. Some of the main ones are really only two main sensors have achieved widespread commercial success. So that's your glucose biosensor, and that's your lateral flow assay, which is also known as your pregnancy test. So only these two have captured large market share. It's sort of at an affordable price point that people are willing to buy, and it's useful to people. Okay, so you have to identify a market that's interested in your biosensor. You have to have a specific analyte that is relevant and important to people, and you have to have a clear-cut advantage over existing methods for analysis of that analyte. So you have to be able to displace other existing technology. Okay. Another thing is that your sensor has to be good for at least 6 months. So you have to be able to store it. People don't want to buy a sensor and then have it sort of immediately expire. And you have to look into things like stability, costs, ease of manufacturing, and finally hazards and, of course, ethics associated with the uses of your biosensor. Okay, so the biosensors, it's a very interdisciplinary field. You have a lot of different components in there. You have to look at your interactions of your biorecognition elements with your biomolecular analytes. You have to look at immobilization of your biomolecules onto your surfaces. You have to develop different surface chemistries. There's your device design. There's your fabrication. You have to integrate your biology with your devices. There's sample delivery, which is your microfluidics, your on-chip electronics, packaging, and different sampling techniques. So your ideal biosensor is something that's going to be very, very sensitive. It's going to be highly specific. It's going to have a linear response. You don't have to make these calibration curves for, like, this is your response for a particular concentration. You want it to be tiny. You want it to be biocompatible. It has to be easy to use, durable. You want small sample volumes. You don't want to have to draw large quantities of blood. You want it to be rapid. You want it to be accurate. You want it to be stable, easily sterilizable because you're looking at biological samples. And, of course, low power consumption is always good. So now I'm going to transition to talking about the research that goes on in my own lab. So this is the platform that we use. It's called the microtoroid optical resonator. It's shown here, and I've put a red blood cell next to it. This red blood cell is to scale, just so you can get an idea of the sizes of these sensors. And it's made of silica. So this region is silica. So this is SiO2, and it's on a silicon platform. And this is basically where your analyte molecules will bind, is along the rim of this resonator. And we're going to go into more detail about how these devices actually work. So these devices are also known as the optical equivalent of a tuning fork. So they have one particular resonance frequency, and when particles bind, they ring or they resonate at a different frequency. So that's where that name comes from. And they're very, very sensitive, so we can detect very, very low concentrations of biomolecules all the way down to the single molecule limit. So you might ask yourself, why do you care about detecting single molecules? So single molecule detection is important for many things. One, fundamental studies. So certain things like looking at protein folding. So protein folding is very important because for this field, form dictates function. So if you're able to control the form of a protein, you can control how it functions, which is important because proteins regulate basically most of the processes in your body. There are things like motor proteins that you can only really look at the single molecule level. Of course, for applied studies, we were just talking about a lot of applications for what these biosensors can do. So you can look at trace detections of markers for diseases. So, for example, tumor-specific biomarkers or markers for things like Alzheimer's. And there's also public health detection of bacteria and viruses. So single molecule approaches are very, very useful because you can directly measure molecular properties. You don't have to take some bulk method, draw some inference, have a model. You don't have to take 1 million molecules, switch them all on or off at once and say this is the behavior of 1 million molecules. Let's divide by 1 million to see what the behavior is for one molecule. And of course, if you can detect very, very low concentrations of molecules all the way down to the single molecule limit, this really reduces the amount of analyte that's required. So that's very important for people whose analytes are very precious, reagents are hard to get, or, particularly for medical diagnostics, you only really want to be taking very, very small quantities of, for example, blood from someone. And of course, if you can really reduce the quantity of substances that you need, this causes a great reduction in cost, which is often very important. And one very important advantage of this sort of technique, this optical resonator approach, is what's known as label-free. And so label-free means that you don't really need sort of to tag the elements that you're looking at. So common tags that people use are fluorescent markers, they're radioactive tags, they're enzymatic labels, they're quantum dots. So you've just recently heard about a bunch of these. But these tags, they can be expensive, they can be difficult to generate. You can't always get them when you want them, where you want them, particularly for these point-of-care applications, or if you're on site at a particular, if you're like on the battlefield, if you're an EMT, you can't always get these labels when you want them. And they're complicated. Studies often require multiple tags. And so this is a picture I put of green fluorescent protein, probably the most famous fluorescent protein out there. And this is interleukin-2. This is a molecule that's typically used in cell signaling. And you can see that if you put them side by side, they're roughly the same size. So if you were to bind GFP to IL-2, you can see that this really might perturb events that you might want to look at. Right? So you can see the ideal approach is a label-free approach, one that you don't have to add these tags to. And things like the microturret can really eliminate the need for these labels. So the current gold standard for label-free biomolecular interaction is the Biocor surface plasmon resonance. So this is a technique that I don't know if you guys remember from Ewan's talk that he was talking about. It's basically you have this gold sensor chip, and light reflects off the back of this gold sensor chip, and it generates an evanescent wavefront. And as Ewan was mentioning, part of your light, at a particular angle, part of your light couples into this gold chip. It's like a surface plasmon polariton, right? And so this changes the angle of minimum reflected intensity that reaches your sensor. And this condition changes as a function of how your molecules bind in your chip. So depending on your molecules binding, number of molecules, type of molecules, this changes the angle of minimum reflected intensity, right, as some of the light is absorbed and coupled into this gold sensor chip. And so anyways, I forgot to mention, Biocor is a company that was sold to General Electric in 2006 for $390 million. So there's, as I was saying, there's very large commercial interest in biosensors. So this is an experiment I did on the Biocor, which I was trying to find the limit of detection, which is what is the lowest concentration of analyte that I can measure using this technique. So I started out at 316 nanomolar, so I basically bound streptavidin to this gold sensor chip, and I flowed in biotinylated protein G, so biotin will bind to the streptavidin. So I started out at 316 nanomolars, and I did a half-log dilution series all the way down to attomolars. And this bottom trace, it says 3.16 nanomolars, but it actually represents 9 orders of magnitude of concentration that you really can't see. It represents nanomolars all the way down to attomolars. But all the traces overlap because the Biocor can't resolve below nanomolars. And so our technique can actually measure concentrations on the order of attomolar. So we're 9 orders of magnitude more sensitive than this technique. So this is our design goal. We want something that's very, very, very sensitive, and this is very, very fast. These technologies on top represent current biosensing technologies. So you can see this is the surface plasmon resonance. So this is the Biocor that I was just discussing. These are suspended microchannel resonators. So this is a beam that's bound on both ends. So you look at analyte molecules which bind to this beam, and you look at the changes in the resonance frequency of that beam as analyte molecules bind. This is a nanowire. This is the lateral flow assay. This is the pregnancy test. That's a paper-based assay. These are microring resonators. This is a quartz crystal microbalance. So quartz is a piezoelectric element. So when particles absorb onto the surface, you can measure the change in mass. This is a biobarcode assay, this is immunofluorescence, and this is a cantilever. So this is just a beam that's bound on one end, and you're looking at molecules binding to this beam, and you're looking at changes in the resonance frequency of this cantilever. And this dotted line represents the present state of the art. And so you can typically see that if you want to have a very, very low limit of detection, so if you want something that's very, very, very sensitive, it typically has a very, very long analysis time. But our technology is both very, very sensitive, and it's very, very fast. Okay, so the microtoroid, it's what's known as a whispering gallery mode resonator, and so they're so named after these acoustic whispering gallery modes, okay? And so this was first described by Lord Rayleigh in 1910. What he did was he stood under the dome of St. Paul's Cathedral in London, which is depicted here, and what he noticed was that whispers at one end of the dome could be heard 40 meters away at the other end of the dome because sound would travel along the edges of the dome with negligible loss. So this is known as the whispering gallery. This is a picture of me and my husband. We were in the Temple of Heaven in Beijing in July. And so you can see I'm here, he's over here. And even though we're far apart, he can hear what I say as I whisper into the wall because sound is just traveling along the edges of the wall. And there are examples of this all over the world, okay? And toroids are the optical analog of this, except you're using light instead of sound. So instead of sound traveling along the edges of an architectural feature, you're having light that's orbiting within a glass device, typically a glass device. So these are optical whispering gallery mode resonators, and they've been made in all sorts of different shapes. But typically when people talk about using these for sensing applications, the three most common shapes that you hear about are the sphere, which is shown here. You have a ring resonator, which is shown here, and you have the microtoroid, which is what I'm going to talk to you guys about today. So this is a sphere. This is not from my lab. This is from Kerry Vahola's lab at Caltech. So it's formed by melting the tip of an optical fiber. And you can see that in this case, it's been doped with a rare earth element erbium, so you can see the light orbiting within the sphere. And what is a little bit difficult to see in this picture is how we couple light into these objects. So light is evanescently coupled in using an optical fiber or waveguide. So you can see that here. This is a finite element simulation of light going into a microring. So the bright colors represent the electric field within these devices. So light is being launched in from the right here. You can see it evanescently couples into the ring. And at the right frequency, which is known as the resonance frequency, you get this constructive amplification of light within the ring. This happens for a particular condition, which is known as the resonance condition, which is if the circumference of the ring is equal to an integer number times the wavelength of light that's going in. And then what happens is we have a tunable laser here. You scan for what the resonance frequency is. You look at when this constructive amplification occurs, and then you can see that as light enters the microring and goes around and around, you see this corresponding drop in the intensity of the light going through the waveguide. And so we monitor the drop in transmission of the resonator, or basically of the fiber or waveguide. And that's how we monitor where resonance is. And finally, this is the microtoroid. That's what I'm going to talk to you guys about today. It's essentially a ring resonator, but it's on a pedestal, so you don't have to deal with light scattering off your substrate. So you're sort of isolated from the noise of your substrate. Okay, so this is just a simulation just to help you guys better visualize what I'm discussing. So you're going to see light being launched in from the right corner. This is a waveguide, and this is your resonator. So light, it's going to couple into your waveguide. You're going to see it go around again. You're going to see constructive amplification in the ring. And then you're going to see a corresponding drop in the transmission of light going through the waveguide. And so once more, right here is where we would put a tunable laser, which we would scan through a bunch of different wavelengths. Here is where we would put a photodetector. So we would measure this corresponding drop in intensity through the waveguide. Right. So let you guys... And so hopefully you're seeing it get brighter as it makes its second round trip. Yes?
What's the purpose of the waveguide going in the opposite direction?
Yeah, so this is actually known as an add-drop filter. So the idea is you can add or drop specific wavelengths. So you can put in many different wavelengths here, but you can select for a specific wavelength out here. So that's what that is. Okay. So these are just to give you guys some numbers. So this is an SEM of what it looks like. You guys already saw that. So they're about 80 to 100 microns in diameter. And it has a dumbbell cross-section. So this dotted line is this dotted line here. So you take this here, you rotate it all the way around, you would get this. So you evanescently couple light in using an optical fiber or waveguide. Light totally internally reflects continuously around the rim of this device, generating this evanescent wavefront, right? So molecules enter, evanescent field. They bind to the resonator. This causes slight changes in the index of refraction of your device. So these are also known as refractive index sensors. And this causes a shift in your resonance frequency. So to give you some numbers, so your toroid has a photon lifetime of 270 nanoseconds. That might not seem like a very long time to you, but in this time, light will go around your toroid 270,000 times, or 68 meters. So you have a single photon. It interacts with your analyte molecule multiple times, and this is what gives us our very, very large sensitivity, right? So molecules bind to this rim. Light goes around and around each time it interacts with your analyte molecule. So what makes detection very, very difficult? So one is that your signal strength scales as r cubed, so it scales with your particle volume. So that means it's 8 times as difficult to detect something half as small. So if you want to detect something half as small, it's not as simple as reducing your signal to noise by a factor of 2. You have to actually improve your signal to noise by a factor of 8, which is actually fairly difficult. So to give you an idea, to detect a 2.5 nanometer radius particle, which is about the size of a single molecule, you would have to resolve a wavelength shift that was less than 0.006 femtometers. Femto is 10 to the minus 15. So that's actually 6 attometers. Atto is 10 to the minus 18. So that's 1 part in 10 to the 12th. So just to give you some idea, some numbers. So for those of you who are in the room who are wearing watches, you might have a quartz crystal inside. So your watch is accurate to 1 second in a month. So that's so that's your watch is accurate 1 part in 10 to the 6, so that's 1 second in a month. So this is accurate to 1 second in 100,000, 1 second in a million months, or 1 second in 100,000 years. So this is significantly more sensitive. In terms of optical frequencies, so atomic clocks have been shown to be accurate to 1 part in 10 to the 18 in a research setting, and in a commercial setting to 1 part in 10 to the 14. So this is something that should be possible to do, even sort of in a complicated environment such as a biosensor. So this is just how we fabricate these devices. So we fabricate them in the clean room here. So we do the first part of the fabrication in the clean room in optical sciences, and then the second part of the fabrication is done in my lab. So we start out with a silicon wafer, has a 2-micron thick layer of silicon dioxide. We pattern circular pads of photoresist. Then we do a hydrofluoric acid etch. So the hydrofluoric acid etches away all the parts of the photoresist. That's all the parts of the glass that are not protected by the photoresist, right? So you're left with all these circular pads of glass that were underneath your photoresist. Then you rinse off your photoresist. And then we do a xenon difluoride etch. So this is a dry silicon etchant. So what it does is it etches the silicon, but it doesn't etch the SiO2. So it'll etch 1 molecule of SiO2 for every 800 molecules of silicon. And so what that does is that sort of creates this undercut and creates these little mushroom-like structures. And finally, our last step is we take a CO2 laser and we fire polish these devices. So we basically use heat and we melt these devices, and surface tension causes these devices to have a very, very smooth surface finish. So this is what prevents light from scattering out and gives us our very, very long photon confinement times. Okay, so here is an array of these. So the idea is, eventually the idea is to have, you have an array of these, you coat each with a different capture agent, so different antibodies, so you can look at panels of biomarkers for particular diseases, right? And so I'm going to show you video. So this is looking from the top. This is a microdisc. This is a top view. This is a disc. So right here is where it's called a microdisc. This structure is called a microtoroid after it's been used to be melted. Heat melts the structure. So you're going to see the laser hit it, and then you're going to see it collapse. And where it flashes very bright white is where it gets very hot. It's like that. So this is the pillar, so you're looking at this from the top. Okay. So from the top view, this is where molecules will bind. So this is just how we do experiments with these. So these are in vitro. This is not in vivo. These are not inside your body. So these are on an optical table in my lab. So this is a rendering. So this is a toroid. This is an optical fiber. You can see this is how particles bind. And so essentially what you have is you have a syringe pump. You flow solutions in. So you take a drop of serum. You take a drop of saliva, tears, urine, anything that has your biomarkers, your analyte of interest, right? You dilute it down into whatever you want to use, like whatever saline solution, for example. You flow it over your resonator. And once again, your resonator has been coated with particular capture agents, right? So antibodies, DNA, receptor molecules, what have you. That makes your device selective for what you're looking at. And so typically the way people do this is they have a laser and they're continuously scanning through a bunch of wavelengths in order to locate where your resonance frequency is. And we do something a bit different. We do active tracking of the resonance, which is we take the resonance of our cavity and we take our laser and we lock it to the resonance of our cavity. And then as particles bind and move our cavity off resonance, we measure the amount of voltage our laser controller has to apply to stay on resonance and follow this event. And then we convert that voltage to a wavelength. Okay. And so this is our technique. This is our advance. We call it FLOWER, which stands for Frequency Locking Optical Whispering Evanescent Resonator. So basically, we have a laser. We have a 50-50 beam splitter. We send half our light to our resonator, half goes to an auto-balanced photoreceiver, which basically subtracts these two signals, so it effectively minimizes noise due to laser intensity fluctuations. We multiply this with a dither signal, which is a small sinusoidal waveform, and this allows us to tell whether we're on resonance or off resonance, and this generates an error signal. And this error signal is then fed into a proportional integral derivative controller, which allows us to reach our set point as quickly and as efficiently as possible. And then it's sent out to 24-bit data processing. So this technique has several advantages. One is that we're continuously on resonance versus scanning past resonance. And another thing is that we're sampling more points per second, which enables us to do more averaging. So this is one application. So we were looking at exosomes. So exosomes are these fluid-filled nanovesicles. They're rather challenging to detect because they're mainly filled with water. So their index contrast is very, very low in their environment. And they're of great interest to people because they're actually they're cancer biomarkers. So they're shed by all your cells, but they carry little bits of the cell with it. But in particular, when they're shed by tumor cells, they carry little bits of your tumor, of whatever the tumor is with it. And so the idea is you look at these exosomes, you take a little bit in your blood, and you can tell, is a tumor present, how much a tumor has progressed. And so this is an experiment which we had our resonator, we coated it with antibodies, we flowed in exosomes. And you can see the way to read this graph is you have your resonators at one particular frequency. One of these nanovesicles binds to the surface, it shifts the frequency to another location, another location, and another location as these individual exosomes are binding to the surface of your device, right? And this is what generates this sort of staircase-like graph. And these bursts in the signal are sort of where we believe these vesicles are trying to bind, but they're not making complete binding events, right? And so you start out, the black is our complete raw data, and then we remove known sources of noise. So we have this dither signal that we impose that we just filter out. We computationally filter all these things out. Okay.
If you are taking like blood, the exosomes,
Yes.
and you can find that there's a tumor present, it
Yes.
doesn't tell you where in the body it is present, but if you took like some other like part of the body, like urine or something, would you be able to more pinpoint where the tumor is located based on that, or is it just like tell you that there is one?
So I think at this stage it might be more like if it's present or not, but if you have a marker for a specific kind, like a lung cancer or something, you might know it's like in your lung. You might not be able to pinpoint like exactly where in your lung it came from, but because it's just shed into your blood and then that just goes everywhere in your body, right? So this is an experiment. This is our sort of one of our first sort of medical applications that we did. So we took human tumor cells, we implanted them in a mouse. So this was human Burkitt's tumor lymphoma cells, and we chose this tumor because it's a very aggressive, very fast-growing tumor. So after about 5 weeks, it's grown large enough that we have to euthanize the mouse, right? And so once more, so we took a little bit of blood from the mouse every week, and so this is actually a bigger deal because usually when people take blood from the mouse, they have to take enough such that you have to sacrifice the mouse. But in this case, we only need to take a little bit, so we're able to keep the mouse alive for longer, right? And mice are sort of very expensive for researchers. So we were able to take blood from the mouse at each week, freeze down all the samples, and then flow them over the surface of our sensor, which once more has been functionalized with antibodies, right? So you can see here at week 0, you don't really see a corresponding increase in signal, but for subsequent weeks, you see a larger increase in the signal as you see larger wavelength shifts, right? Presumably, as more of these biomarkers are binding to the surface of your device, right? So for later weeks, you have more of these biomarkers present, so you see this larger signal increase. And this is a control experiment we did with a mouse of no tumor, so you don't see the same corresponding increase in signal that you see as you see with a mouse with a tumor. So that's one control that we do. So where do we go from here? So there are a lot of places that we go from here. One is that we have projects looking at further improving the sensitivity of our devices, further improving our selectivity. We're looking at early detection of Alzheimer's, early detection of cancer. We have a project on performing enhancing drug detection. So with events like the Olympics, there's a lot of money and national pride tied up into these events. Athletes do things like they microdose, which is they dope right beneath the detectable limits of sensors. So it becomes a game of how good of a sensor you can make. They also take diuretics to really dilute the concentration of drugs in their urine. So that's something that we look at too. portable diagnostics. We're interested in making these into like handheld devices such that you can give them to soldiers on a battlefield, EMTs and ambulances. We're looking at chemical threat safety. There's a bunch of environmental monitoring that we're doing, also looking at water safety, food safety, and basic biological functions. So I'd like to thank the following people, my current funding sources, and I'm happy to take any questions at this moment. Yes? Yes?